Welcome to episode 2 of Light.Conversations. Thank you for joining us on YouTube. This edition is also available on a podcast. My name is Constantine, and welcome, James Portman.
Hi, Philip. Nice to see you again. I wonder what we're going to talk about today.
Well, I tell you, the following last week's conversation, the natural progression for us was, what is a laser? I had a chat this morning with my 9-year-old daughter, and she said to me, Dad, is a lightsaber a laser? And I was wondering, what are your thoughts on this, James?
Yeah, I guess that the popular concept of what a laser is versus the reality from an engineering or from a physics point of view, they may be two completely different things in some respects. The very notion of being able to hold a laser in your hand and wave it around and see a beam of light and so on, it's a cool idea, but that doesn't mean that it's a laser. A laser has very specific characteristics to it. And interestingly enough, none of those characteristics would make a lightsaber. So I guess what we have to do here is dissect the difference between a popular version of a laser and an engineering version of a laser. Sadly, the engineering version may be a little more boring than the popular version. But
let's start with the word laser. I mean, light amplification by stimulated emission of radiation. I mean, what do all these words mean, and how does it all come together?
Sounds almost pornographic, doesn't it? But it isn't. It's about a light amplifier. We're kind of used to the notion of an amplifier being used in the context of electronic circuits. So, for example, you would have an audio amplifier or a voltage amplifier or something like that. And the idea is that you start with a small signal, you apply some power to it, and what you get out is a larger signal. The same thing is true for a laser amplifier or a light amplifier. The idea is that you start with a small amount of light. Think of it as a seed, if you like. And you try and construct a machine made out of the laws of physics and the laws of chemistry, such that when you pour more energy into the system, you get more light out of the system. And surprisingly, there are lots of different ways of doing this. So you can end up with lasers that are absolutely enormous, complex arrangements of mirrors and optical resonance cavities and chemicals and so on.
Wow.
Or you can etch it onto a chip as a tiny little light source that can be used for optical communication. They're very different in construct and very different in the way that they actually work. So the only common feature of all these different lasers is the amplification element, that you're amplifying light, not amplifying electricity.
Oh, interesting. So let's explore that for a second. If we talk about amplification, is it about focusing the beam, or is it about aligning the peaks in the wavelengths of the wave of light?
Certainly, one of the ways of improving the amplification is to use what's known as a resonant amplifier. In the same way that most mechanical objects have a resonance frequency, which makes them more efficient and more effective, so you can design a laser with a resonant cavity to it. And the resonance cavity uses the natural interference of light with itself to improve its own efficiency. However, It doesn't mean that you have to do that. It's just that in the process, you generate a more efficient kind of amplifier. But nobody says your amplifier has to be totally efficient. It just needs to have a gain slightly more than 1. And as long as it's got a gain of slightly more than 1, then it's an amplifier. It's as simple as that. So whilst it's true that most lasers will have resonance cavities in the forms of mirrors on the end to send the light backwards and forwards so it keeps on amplifying itself, that's not true of all light amplifiers. You now have fiber-optic amplifiers, for example, where you put the light in at one end and it just comes out the other end bigger. And there's no need to have a complete resonance circuit in there. Does this necessarily create a parallel beam? Well, it turns out if you have a very high quality, what's known as a high Q resonance cavity, then you tend to get a parallel beam out of it. But if you have a lower quality cavity, then the beam is not so parallel at all. In fact, in many lasers, the beam comes out with a divergence of anything up to 30 degrees or more. And it is not the parallel, science fiction vision of lasers that we imagine.
Interesting. Well, if we think about the use of lasers today, lasers are used to measure distances to the moon. They used to blow things up. They used to cut through diamonds. We use lasers for all different kinds of applications today. But what are those common characteristics within laser beams that are common to all of these different applications?
Now, to me, this is such an exciting question because whenever you're looking for an engineering solution to a problem, what you want is you want to apply the correct science in a way that gives you an effective solution. Now, when you look at a laser and you say it's a light amplifier, how can you say that that's an effective solution to measuring to the moon, for example, or for cutting a piece of steel? There must be something else about the concept of a laser or about the physics of a laser, which has a different characteristic that can be useful in those cases. So it turns out that amplifying light also allows you to amplify the energy that is associated with that light, to take it to such high levels that you can cut through a piece of steel, for instance. But that's not terribly useful if you want to send information down a fiber optic. So the characteristics that you need for a fiber optic are a very confined wavelength so that you can send multiple laser signals down the same piece of fiber at the same time. So what you're looking at there is what is known as the coherence, or if you like, the frequency stability of the laser. So here are two characteristics. One is energy, the other is frequency stability, which are completely different in the way that they are applied. And there are more characteristics as well. For example, most people don't realize that when you do apply the energy to a laser system, that the amplification process is incredibly fast. So for example, by comparison, if you take an audio amplifier, it will amplify signals up to maybe 30 or 40 kilohertz. When you take a light amplifier, it amplifies things at such an incredible speed that sometimes within a few picoseconds, you can already have full amplification from zero, which means you can generate flashes of light. So often lasers are used to generate very short, high energy flashes. And again, you can choose what energy level you want. You could have a low energy device, which is what is used in a LiDAR system, or you can have a high energy device that they use for what's known as surface ablation, where they modify the surface of hard materials. So it turns out there are lots of characteristics of lasers. Small size in some cases, large size in other cases. Parallel beams sometimes, non-parallel beams other times. And depending on the solution that you're looking for your engineering problem, you would choose the characteristic that is most appropriate to solve that particular problem.
That's interesting. Let's consider for a moment, I mean, if we look at the Curiosity rover that went off to Mars, I remember hearing that the Curiosity rover actually had a laser spectrometer on board. So what characteristic of lasers would that be drawing on to be able to derive that intelligence from the surface of Mars?
Yeah, in that particular case, what they wanted to do is to vaporize materials. So they were using the energy content and then looking at the spectrum that they got out of the materials as a consequence. In many cases, laser spectrometers also use multiple wavelengths, because that way you get more than one signature. If I recall correctly, the next Mars rover uses a 4-color laser to do its laser spectrometry. So again, what a fascinating use case. And clearly nothing to do with lightsabers or a red light, because in many cases the wavelength that is chosen or the frequency that is chosen is invisible to the human eye, and yet is far more useful from a spectrographic point of view, because chemical resonance frequencies are not always in the visible wavelength anyway.
Right. So maybe just talk to us about the different colors of lasers and the different energy levels one can expect to derive from these different colors of lasers.
Yeah. So it turns out that lasers these days are available in many different colors or many different wavelengths. In the good old days of the 1960s, you were pretty much stuck with red and some infrared type lasers. But now the material processing has improved to the extent that we can generate this optical amplification effect in many different materials. And each material has a natural ability to produce a particular color. So we can go all the way from ultraviolet lasers right through to far infrared lasers. And by choosing the wavelength, you can also pick the way that light, because we're only talking about light energy here, really, you can pick the way that it interacts with solid materials. So for example, ultraviolet lasers tend to be fairly aggressive in the sense that they can be they can cut things, they can burn things, they can generate a lot of energy. And it's because the wavelength is very short. It's a very high energy wavelength.
Yeah.
But you can have infrared lasers, for example, which even at high energies are perfectly safe. For example, they may be eye safe or they may be safe to the skin. And there are certain wavelengths which are almost completely safe. This is not a simple equation in saying that the longer the wavelength or the lower the frequency, the safer the laser is. There are peaks and troughs in susceptibility in terms of, let's say, organic materials. So by picking the right wavelength, you can have two benefits. On the one hand, you can make something very safe if that's what you're attempting to do, or you can make it very dangerous if that's what you're attempting to do. At the same time, you can pick a fabrication methodology, in other words, a method of assembling the laser system, which is either very inexpensive, such as a little laser pointing device that you might use to give a presentation, or you can end up with something that is incredibly expensive and incredibly difficult. For example, they can make lasers using uranium extracts. And these are pretty exciting on many different levels of danger, as you can imagine.
I love that. Thinking back to varsity, I remember we had a laser in a room. This laser took up most of the room. There were rubies involved somewhere, and it had all these mirrors with beams flashing up and down and reflecting. And there were cooling devices, and it was really a magnificent piece of equipment. I wonder how we've moved from those kind of massive laser constructions to, I remember meeting with you in the office a few weeks ago, and we were looking at the laser diodes that are present in the LightWare LiDAR systems. How have we moved from the need from reflective mirrors and lining things up and finding beam coherence through reflection to something that's really smaller than a thumbnail?
It's perhaps one of the few areas in laser technology where significant advancements have been made, and that's on size. The physics behind it remains the same. It's not as if we've suddenly invented something that is dramatically different in the way that it works. So even a very small laser diode has a resonant cavity of some sort. It has mirrors, which they call facets, on the ends of this resonant cavity. However, what they've been able to do is to make use of a little bit of quantum physics to improve the efficiency of the amplifier. And many of the lasers that we use these days are known as multi-quantum well designs, where they constrain the light inside this quantum valley. And by holding the light tightly within this valley, it amplifies more quickly because you don't lose as much light through leakage and things like that. So these small devices are extremely clever, and it's testimony to the quality of the fabrication that we can do these days on semiconductor materials. In the end, though, it's horses for courses, because there are only a certain number of wavelengths that can be created using a simple semiconductor material. And if it happens that you need a different wavelength, then you need a different kind of fabrication process. And inevitably, the one you're looking for is always 10 times bigger than you need, but such is the world of engineering. So the moving away from these multiple mirrors and so on, I think has been an important stage in terms of the commercialization of laser technology. But some of the best lasers that are still available today still have these optical test bench appearance with wonderful mirrors and cooling systems and so on. And I was quite excited talking to the guys at NASA about their lunar laser ranging program, and they were showing me their optical test bed. And it had a frequency doubler in there where they were taking infrared laser light and turning it into green laser light. But it wasn't very efficient, and generally there was a lot of energy that kind of disappeared during this process. And they said they had to be very careful about where that energy was directed. And they related an experience where the guy was standing next to this device with drinking his cup of coffee, and he could smell burning. And next to him, the filing cabinet was set on fire because the excess light from this laser system had leaked sideways and had gone where it shouldn't have gone. So these devices can be incredibly powerful and incredibly dangerous. And yet at the same time, they can also be very safe. They can be used for eye surgery. They can be used for, quantum communication and so on. So it's a wonderful world we live in when we talk about lasers.
That's amazing. I'm pleased to say that we don't have those kinds of incidents in our office. It would make it precarious. So if I were to take apart a DVD player and I pull out the little reading laser and I have a normal LED light emitting diode next to that, they pretty much look the same. What are the differences? Because if you, I mean, both of them emit light. How is the light changed as one moves from a normal LED to a laser LED?
There are really only two fundamental characteristics that are different there. Even the fabrication process is very similar in terms of the material science. In the case of the laser, it has some kind of mirrors on the end, some resonance facets, which allow the light to operate in a much narrower wavelength band. So an LED tends to have a fairly broad spectrum of light that comes out, whereas the laser has a narrower spectrum. It tends to be a characteristic of any resonant amplifier, is that a resonant amplifier always has a preferred frequency of resonance. The second characteristic is the light pattern. Interestingly enough, the laser light that comes out of the small semiconductor lasers is not a parallel beam. It actually expands quite rapidly once it comes out of the front of the laser because it's not a particularly efficient resonant cavity. So in the same way, the LED light also spreads out. The difference is that the light that comes out of an LED comes out over a fairly large area. It can be anything up to 0.5 millimeter to 1 millimeter in diameter. The light that comes out of these small lasers comes out of a very small spot, tiny, tiny little spot. And what that affects is the ability to focus that light down to a point. Now, when you're looking at a DVD player, it's the focus that's the critical element there. You need to be able to look at a specific pixel on that DVD player and be able to tell whether it's a 1 or a 0, which means you need to be able to focus to a tiny little spot. If you use an LED, you'll find that the laws of optics unfortunately fight against you and prevent you from having a perfect focal point. Now, there are degrees of perfection on these things, and again, like all engineering problems, we have to pick the point of compromise that works best. And it turns out that DVD players have been extremely successful in the way that they've used lasers. I'm amazed at what they've managed to achieve with relatively inexpensive devices. And it's really changed our world. And I guess this is where this story leads, that whilst the characteristics of lasers in their own right don't seem to be particularly magical, you can make a parallel beam or you can make an expanding beam. You can make a pure color or you can make a slightly impure color. You can have a large laser, you can have a small laser. It can have high energy, it can have low energy. In that respect, that doesn't really explain why they have become such powerful tools in everything that we're doing today. Until you realize that each of these characteristics can in some way be tamed and applied to very specific problems. It doesn't mean it's a solution to every problem, but the high energy allows you to cut things if that's what you want to do. The high speed allows you to have very fast fiber optic communication, or in the case of LiDARs, it allows you to get accurate LiDAR measurements. The individual color allows you to manage safety. It allows you to manage multiplexing of different colors, and so on. And almost every characteristic has been exploited in some way or another in trying to create a commercial and viable product, which otherwise would not be possible.
Wow, that's a huge array of possibilities. James, I think let's leave it there for this week. I think a natural progression for us moving into next week would be to take this concept of a laser and explore how we specifically apply that within LiDAR devices and the characteristics that we draw on to make the LiDAR devices work and eye safe.
Can I say what a brilliant idea, Phil? I'll speak to you next week.
Great, thank you.
Bye-bye.
As always, thank you, James. As always, the content is available on our website. Please visit www.lightwarelidar.com. If you'd like to comment, please drop us a note on social. And if there are any particular topics that you'd like to explore, please feel free to leave notes on social. Thank you so much for your time and see you next week.